Okay, so that was the line that should be closed. Okay, so today we're going to talk about derivatives in this Riemannian geometry, differential geometry sense. So the lecture's on covariant differentiation. And before we start, let me give you a more or less high-level summary of what we have done so far. The state of affairs at this point. Okay, so up to now we've studied a bunch of preliminaries and then moved on towards studying extrinsic geometry of surfaces. So this extrinsic geometry is encoded in the variation of the normal vector field, so derivatives of the normal vector field. You've seen this picture before. The derivative of the normal vector field along a curve tells you, along a specific curve, tells you something about the radius of curvature at that point in that given direction. So a circle is a one-dimensional object. You sort of align it along the surface in the direction of the curve given, and the radius of the best circle, the largest circle you can fit there, the optimal circle, which makes optimal second-order contact to the surface, is has a certain radius. And that radius is 1 over k, and k is the so-called principal curvature in the direction x. So the variation of the unit normal vector field gives you this information. It's encoded in the matrix or the tensor called the second fundamental form. From this you extract these invariants called the mean and the Gauss curvature as the trace and the determinant of the shape operator. All right, so this is the information extracted from the second fundamental form, and basically what it tells you is gives you a local characterization of the shape of the surface extrinsically, so as it appears in three-dimensional space, as it appears to the outside world. So you distinguish between all positive curvatures, one positive, one negative curvature, and then more interesting things can happen when you have a zero curvature direction. Okay, so this is what the extrinsic geometry does and how it's encoded. And the big picture is it tells you the way the surface looks like from a distance, from outside. So the next, then we move forward and we started talking about the so-called intrinsic geometry of the surface. And well, we just started and I haven't quite justified the name yet, that this is something special and different. But in any case, where we began was, we talked about the induced metric. And this is the inner product of Euclidean space, except viewed from the tangent planes of the surface themselves. So in other words, you consider it sort of as an operator, the inner product restricted to the tangent plane as a bilinear form on a product of two-dimensional vector spaces, right? So it operates on vectors that are two-dimensional and live in the two-dimensional tangent plane of the surface. So this is our first step into the intrinsic geometry, defining this induced metric. And of course, we saw that it pulls back under the parameterization, under any given parameterization, to this object here. This is the matrix of, the derivative matrix of the parameterization transposed times itself. And it was the matrix constructed from the inner products of the basis vectors. So this was not necessarily a diagonal matrix, and so it's not necessarily a standard inner product. It was an inner product that was different depending on which you were at. But nevertheless, it's a positive definite, strictly positive definite matrix. It is the induced metric, but viewed from the parameter plane itself. It's like from inside the surface, or at least from inside the parameterization of the surface. And now, as I said, I haven't justified why this thing should have a special name, the intrinsic geometry and all that. All we've done so far is we've seen that intrinsic lengths, so in other words, the lengths of shortest paths on the surface, the geodesics of the surface, can be expressed in terms of this induced metric. So my picture here shows that. Here I've got my parameter plane and a parameterization mapping into some surface. Here's a curve along the surface. And I've written this curve in two ways. I've written it as gamma, which is the curve in the surface. And then I'm also writing it as C, which is a curve in the parameter plane, but pushed forward under phi. So in other words, I'm writing gamma as phi composed with c. Takes the curve c and moves it forward. So I got the curve written in two different ways. One on the surface and one in the parameter plane. And what we showed last time was that you could write down the length of this curve in two different ways. Well, I guess we showed this form of the length a couple weeks ago. The length was the integral of the length of the curve is the integral of the norm of the tangent vector of the curve. So right, this object here is nothing other than the length of the tangent vector of the curve, magnitude of the tangent vector curve. Or you can pull all of this back. You can pull this entire formula back into the parameter plane. And therefore you can express the length only in terms of the objects which exist in this parameter plane, in the curve C, and this parameterized version of the induced metric. So you just rewrite exactly this formula, do the change of basis and change of variables and so on, and you get a formula for the length which looks like this. It's the tangent vector of the curve over in this parameter plane, inner product with the tangent, with the length of the tangent vector, but with respect to this G inner product. So this is a triple matrix product. Here's a 2 by 2 matrix. Here's a 1 by 2 vector. Here's a 2 by 1 vector. So this is the inner product with respect to the matrix G. Okay, so sure, the intrinsic metric, which I've given this great name, appears in length computations. So this is where we left Monday of last week with defining the intrinsic geometry. Okay? So one more thing about last week's lecture, which is a loose end. So in last week's lecture, we derived the geodesic equation. Right? We derived the equation that a length minimizing path on the surface S has to satisfy. And that equation was the so-called geodesic equation. It says that the curvature vector is perpendicular to the surface. So since there's no picture on here, let me just draw that real quick. So here's my surface. Here's what I'm going to, well, I don't know if it is or isn't, but it doesn't look this way, but let's say that this is a length minimizing curve. This is the shortest path from P over to Q on the surface. There's no quicker way of getting there unless you leave the surface. And the geodesic curvature vector is this vector which points orthogonal to the curve. So this is the curvature vector gamma. It points orthogonal to the curve. And here's the normal vector of the surface. Let's put this down. The geodesic curvature vector points orthogonal to the curve, but it doesn't necessarily point, it's not a vector, it's a vector in a three-dimensional space. It's not necessarily related to the surface just yet. Right? It's just, you could take the surface away, the curve would still be there, and its geodesic curvature vector would still be there. It has nothing necessarily to do with anything. So a priori, you just see this k vector just sitting off in space somewhere. In particular, it doesn't have to be in any nice relationship to the normal vector. It doesn't have to be parallel, it doesn't have to be perpendicular, it just points in some direction. Okay? But we derived that if gamma is the shortest path in the surface, then this k vector is in fact orthogonal to the curve, which means it points in the opposite direction of the normal vector. Okay? So in fact, the k vector is normal to the surface. It is perpendicular to the tangent vector. This is what we derived last week. Yeah.
So k vector is perpendicular to the tangent plane or perpendicular to the normal?
Parallel to the normal.
Parallel.
Yeah, so perpendicular to the tangent plane. Yeah. Okay, so the loose end. So I'm trying to sell you on the idea of intrinsic geometry. And the loose end is that this equation here looks like a completely extrinsic thing. It seems to depend on the normal vector of the surface. And of course, it's computed using the k vector of the curve, which already is something which you shouldn't really associate with the surface, you should associate with the curve. So it looks extrinsic. So what I'd like to do today, today's lecture, the purpose of today's lecture is to resolve this ambiguity. And, well, we're going to do, well, okay, so the primary, I guess there's two ingredients today. The first is, I want a way to introduce this new topic, because it's very important in its own right, covariant differentiation. But my way of introducing it is, in order to resolve this ambiguity, I'm going to show, by means of a proper study of how to differentiate things on a surface, I'm going to show that this equation up here, even though it looks extrinsic, is actually an intrinsic thing. It can be, in other words, it can be expressed in terms of G alone. And actually, you will see again in the lecture that the expression we get is a system of second-order ordinary differential equations. And that's actually very good from a theoretical point of view, because actually another loose end from the previous lectures, which we didn't really discuss at all, is the existence of geodesics. Okay, you kind of think they exist because they're short, you can talk about them geometrically. But in order to prove they exist, you have to solve something, solve some equation. And the fact that we can reduce the curvature, the geodesic equation, to this system of second-order ODE is really good, because there's a good theory of solutions of second-order ODEs. So actually, the theory of geodesics works with that system of ODE to prove that geodesics exist. They're of a certain length, and they're smooth, and all this. So the fact that we get an ODE out is a good thing. But anyway, we're not going to talk about the ODE too much. We're just going to get to this point. We're going to show that this seemingly extrinsic equation is intrinsic and can be expressed in terms of geo. Okay? So that's the plan for today. Any questions so far on the previous material or our new direction here? Oh, yeah.
Sorry, I just picked up on something. You're trying to sell us an intrinsic geometry. It seems like there's a value to that just because it's more practical to work on parameterization than like a bi-parameter parameterization.
So often it is better to work in a parameterization. Yeah. So in fact, I don't want to take you. Let's say I don't want to sell it to you to the exclusion of the extrinsic geometry. I want you to have both tools in your toolbox.
Understand.
And I would say this is an example of why intrinsic is good, because you often, the stuff you can actually solve, and get your hands on, get your hands dirty with and solve, happens to be in the parameter domain always. Yeah. Okay. So next, right. So before we get there, we have to talk about. Before we get to my final message for the day, we have to talk about differentiation. So I'll take the rest of most of the lecture. Here, this is us.
That is us, actually.
I saw 468.
Which is this class.
Yes.
So a quick reminder, this is a good point as any, that your homework 2 is due today. Homework 3 will go out hopefully later today, as will your project instructions within the week. So check the course webpage for that, and carry on.
Yeah. Okay, so did my near somersault in the class get deleted from the video?
Absolutely not.
And presumably this brain lapse isn't going to get deleted either. Right. Oh. Okay. Yeah, so where are we? Okay, so differentiation. So we already know, we were talking about differentiation, but actually we've talked about differentiation of scalar functions. And what we're going to do next is talk about differentiation of vector fields. So this is in fact a crucial difference, which you'll see on the next slide. But first, let's just go through this differentiation in Euclidean space. Okay, so the way we do it in a geometric way is we always make this assumption upstairs, which is we want to associate differentiation in three dimensions. We want to associate multidimensional differentiation with a direction. Okay, so given a vector in R3 somewhere anchored at the point P, so here's your picture. Here's Euclidean space. Here's R3, here's a point P, and then I want to say that there's a vector attached to point P, right? So there's that. Okay, so in order to make differentiation geometric, we always have this picture. We have a direction vector, and we have a curve which passes through the point P in the direction of V. So the tangent of the curve at the point P. So what's my curve? Gamma or is it C? C, right? So I want C at 0 to be P, and the derivative dc by dt at 0 to be the vector v. Right, so when you talk about derivatives in a geometric way, you always associate the direction, but that's somewhat not enough. You want to associate the curve that moves through. Okay, and now the derivative of a scalar function in the direction of the vector v is now an easy thing. You evaluate the scalar function f on the curve. So you look at f of c of t, which is f on the curve. And then what you do is you take the derivative, f of c of t, and you go to the point of interest, namely t is equal to 0, and this is your definition of the derivative in the direction v of the function f. So actually, it's another way of looking at this is it's another way of saying this is it's the derivative matrix of f transpose times the vector v. That's just another way of writing this formula down. All right. The inner product of this df dxi with vi, but of course df dxi is a column, so you make it a row by taking a transpose. That's the formula. Okay, so this is derivatives of a scalar function in the direction of a vector field. Now it stands to reason that you have a formula, there's a reasonable formula for the derivative of a vector field, because a vector field is just 3 scalar functions in a row. So it stands to reason that the derivative in the direction v of the vector field y should be the same formula stacked 3 times. All right, so how do you get this formula? Well, you do the same procedure as above. You evaluate the functions y1, y2, and y3 on the curve, and then you differentiate it t equals to 0. Out comes the, why are there little angle brackets here? I'm not sure. Anyway, out come the 3 different derivatives of the 3 different components of the function, functions, y1, y2, y3. Okay? So this is how you differentiate vectors in R3, and functions and vectors in R3. So it fits together nicely. Okay, but the picture on a surface is a bit different. So let's just walk through here. Okay, so first of all, scalar functions on a surface. Well, there's no problem there, because you use exactly the same formula. You can evaluate f on a curve, except this time you just imagine that the curve you're interested in is living on a surface. And the vector v belongs to the tangent space of the surface. Right, so if I just, maybe, I shouldn't do it this way, but if you just erase all the stuff that refers to R3 and replace it with surface stuff, then the formula works fine. Because it's completely reasonable in geometric to think of a curve moving in a surface, and the tangent vector of that curve is the tangent vector of the surface. Like the first order, these things are all the same. The first order in the Taylor series sense of first order, everything's the same. So differentiation of scalar functions on surfaces, completely fine. Okay, so now we come to this, the key problem, which is let's try to do the same thing for vector fields on the surface. And now you have this problem. I'm not sure if I can be able to successfully draw a picture of this, but I'll do my best. Okay, so the fact of the matter is, this vector field here has no, once you differentiate it, right, once you differentiate it, that the vector you get out has no reason whatsoever to be tangent to the surface S. So yeah, this is some kind of operation you do in vector fields, but you can't think of it as an intrinsic differentiation on the surface because the object you get out doesn't live on the surface anymore. Okay, so here's my best attempted picture. So here's my surface. Get rid of the little small guy up here. Here's my surface, and the red isn't working so well. So here's my surface. Here's a curve in the surface, and here's the tangent vector of the surface. So this is v, and let's consider the vector field y. What does the vector field y look like? Well, it's a vector field which lies on the surface. So it's like, I don't know, something like this, right? something like this. But the point is that these vectors here have to be parallel to the surface, tangent to the surface. All right. Okay. Yeah. Okay. So right. So what am I doing when I differentiate in this direction? What am I actually doing? Well, let me. And I want to somehow convince you that the vectors aren't going to be tangent necessarily to the surface. So how am I going to do that? Well, what I'm going to do is I'm going to take a sort of a one-dimensional slice. I'm going to take a slice through here and draw over here exactly just what's happening like a plane, like a transverse slice to the surface. So let me take a knife, a surface knife, and let me slice through this curve. Let me slice through this curve, and let me move this slice. It's like an MRI, medical imaging. I'm taking a slice through the surface, and we're going to study it. Okay? So here's my slice through the surface. Here's the surface viewed edge on, and this is the curve in the surface. And what am I doing? Here's my tangent vector, right? Here's my tangent vector of the surface. I hope this works, by the way. Okay, so what do I have to do? Here's a vector. Here's a vector which is like tangent to the surface. Here's a vector which is tangent to the surface at this point. Here's the next vector which is tangent. So this is the vector y at c at 0. Here's the vector y at c of little tiny delta t. Okay. Do you see what I'm seeing? I see something when I look at this board. Do you guys see it too? Do you guys see what I'm seeing? So this vector is kind of pointing out at you, right? It's one of these red guys. It's one of these red guys. So if I were to take this slice and rotate it towards you, you would see this picture. Does that make sense? Can people nod or shake their heads? Because I'll do something to make sure you see this properly. Okay, so how do you take a derivative? What's the operation sort of that in your mind happens when you take a derivative? Before you take that limit, what's going on? You know, a derivative is a limit. What happens? What's the thing that's happening?
Final minus initial over step.
Yes, final minus initial. So I want to take this vector minus that vector. What does that look like? Well, okay, so let's take this vector and move him over here. So minus initial is this little stub right there. And this little stub right there, okay, now my picture is even not helping at all. This vector here, that final minus initial, the next thing that happens is you divide by the distance, right? So you just take the limit and it gets shorter and shorter and shorter, right? It's longer and longer and longer. Anyway, it's a very short vector. The vector's getting closer. But in any case, that direction stays fixed. Is that green direction tangent to the surface anymore? Well, not necessarily, right? So this is what this picture is supposed to convey. Yes, the two red vectors themselves are tangent to the surface, but because they're slightly shifted off from each other, when you do final minus initial, and you subtract them, you've got an offset vector. And that offset vector can be anything. Right? So this is somehow my attempt to convince you that this statement is true here. Is that the reason this is not true is y final minus y initial. That offset may or may not point on the surface. It has no reason to point on the surface. Yeah, Fred?
Why does the vector field need to be tangent to the surface in this case?
Because I'm trying to define a notion of intrinsic differentiation, which reflects the surface itself, a two-dimensional version of differentiation.
But you could be measuring the change of a vector pointing in some arbitrary
You could.
direction.
Yes.
As a function of motion along the surface.
You could do that. Yes. Yes. There's a different way of, a different type of derivative on a surface, which is the vector field can point anywhere, but it's just restricted, tied to the surface, and then you differentiate along the surface directions. So yeah, you can do that. That ends up being some kind of hybrid between three-dimensional and two-dimensional differentiation. But it's more in the camp of three-dimensional differentiation, except this idea of being restricted to not a curve, but a surface in this case.
So we would call this two-dimensional vector field.
Yeah.
Differentiation.
Yeah. And which often you need. Like often the objects of interest live on the surface itself. and you want the rates of change on the surface itself. So often you need to think of it in those terms. So is this vaguely convincing to anyone? Okay. If not, I admit these are kind of crappy pictures. There's not enough dimensions on the blackboard here. I'm happy to redraw them afterwards. Okay, so we're at this point here. I'm saying we have a problem doing the 3D version of, importing the 3D version of derivatives to the surface because the differentiated object is no longer tangent to the surface. This is an issue. So, well, okay, so how do we solve this? What are the alternatives to this approach? This is like the most reasonable thing out there, so what are the possible alternatives? Well, first question is, can we come up with a geometric definition, some kind of geometric alternative? Because after all, that's the kind of thing we're after. We're after things which are independent of parameters, things which have a geometric meaning. So can we come up with something? And maybe we can't, so we have to go use a parameterization instead. But now we face the problem of whether or not whatever definition we decide on is independent of parameterization. Remember, we always have this issue, right? So we have to do some proving to show that whatever we come up with is independent of parameterization. And a hint that it's going to be difficult is that, I mean, it looks like we may have to differentiate the coordinate vectors, right? The fact that if you use a parameterization, every point on the surface has a different basis, right? So how do you compare vectors? How do you do final minus initial when at the final point and at the initial point, you're using two different bases to express vectors? Well, you can do it. You just have to differentiate the basis vector fields too. Anyway, so you can see, well, I'm trying to say that there are probably going to be complications if we go in the parameterization direction, which we would then have to deal with. Does that make sense? Let me just reinforce what I said about differentiating the parameterization with the picture, because actually, I'm not going to talk about it more, but it is still something important to realize. If this is your surface, and you have a parameter domain down here, and your parameterization, then you have the vector field, you have the coordinate vector fields, right? You have 1, 0 transpose and 0, 1 transpose. You have the coordinate vector fields, and they're constant everywhere. Like down in the parameter domain, that's a square coordinate chart everywhere. So doing final minus initial when it comes to doing vectors is no problem. Same coordinate system everywhere. But if you push this forward on the parameterization, right? You move it to different places. These vectors, these two vectors, they're different from place to place, right? They're different from place to place. So if I wanted to do final vector, suppose I'm at this point here, and I want to do a final minus initial type of calculation, and I'm trying to compute, I'm trying to do it for a vector, right? This vector y, at the final point would be expressed in terms of this basis, and at the initial point would be expressed in terms of that basis, and they're different bases. So doing the subtraction has got an extra level of complication. Does that make sense? Okay, so we're not going to talk too much more about this, but it is something to realize. The basis changes from point to point. Okay. So that's what I want to do. Okay. Right, so this is it. This is the issue, so let's move to the next slide. Okay, so the way we're sort of define covariant differentiation for you. And it turns out we can take a geometric route. We don't have to use parameterizations just yet. We can define covariant differentiation in terms of in a geometric way. And actually, it's kind of a very cool thing, except that's wrong. Oh my goodness. Okay, that is wrong. I feel the need to change the slide because this is so egregiously wrong that I don't want to. This needs to be deleted from the video. Yeah, that needs to be deleted from the video. Okay, we're back. Brilliant. Okay, back in business. All right, where were we? Okay, so have a geometric definition. What is it? It's the cut. Where did it go? Nice. Yeah, it's the nicest, simplest thing you could imagine, you could ask for. So remember I said that the derivative vector y may or may not be parallel to the surface? It might just point off into space somewhere. Well, here's the definition of covariant derivative. Take the derivative dvy in the Euclidean three-dimensional way. That's a vector which points wherever it wants to. Take the parallel part, project it onto the surface. So that's why this is egregiously wrong, because it used to be perpendicular up there, but now it's parallel. So the picture is, right, here's your surface S. Here's your curve, here's your point P, here's your direction V. Then you have this vector field, which I'm just measuring, it's everywhere, but I'm measuring it along the curve, right? And then, is there blue over here? And then my covariant derivative is going to be, I mean, my ordinary Euclidean derivative, let's say, is, maybe not this big, is this vector here. This is dv of y, and this is not parallel to the surface. And then you project it down, right? You project it down. This is nabla, or del v of y, and this is parallel because it's projected. So I'm just projecting it down, taking an orthogonal projection into the tangent plane of the surface. Okay, and by the way, this thing is pronounced either nabla, well, the letter, the symbol is a nabla. This upside down triangle is a nabla, and this thing is usually pronounced del v of y, or del y, or something like this. Or if you just want to, not shorthand, to say the covariant derivative of y in the direction of v. Okay, so this is it. So yeah, like I say, this dv of y is just the ordinary Euclidean three-dimensional derivative. Okay. Right, and now notice right away I have this nice relationship with the second fundamental form. Right? The second fundamental form used to be the perpendicular part of the derivative. Right? It was the perpendicular part of the derivative. Well, in fact, we defined it a little bit differently. We defined it in terms of the normal variation. It occurs to me we may not have written this formula down. Do you remember this formula? I can't remember if we did it or not. I'll do it again. But in any case, okay, so let me say this last part differently. Let me say that now we can express the Euclidean three-dimensional derivative, stand over here, Euclidean three-dimensional derivative in terms of the parallel part, which is the covariant derivative, and this thing, which is the normal derivative. The normal part of the derivative. And since I can't remember whether or not we did this calculation, let me just do it right away. Let me do it right here. That is, well, what is this normal part? Well, it's dvy, take the inner product with the normal vector. Now, remember the usual trick. The usual trick is to use the product rule. Right? I can write this as the derivative, so this is like, it's like dv of the inner product y with n minus the inner product of y with dv of n. Right? And because y is parallel and n is normal, this whole thing here is just 0. And you're left with just this. But this here was our definition from several weeks ago of minus the second fundamental form. It was the derivative of the normal vector in the direction v, take the inner product with y. So this was actually, so this is minus the second fundamental form of yv. Or in other words, it's just the second fundamental form of y and v. So, consequently, this first piece of the Euclidean three-dimensional derivative comes out here as the second fundamental form. Okay, so just using orthogonal decomposition, I have this nice formula, which is Euclidean three-dimensional ordinary derivative is second fundamental form term plus covariant derivative term, normal part parallel. Okay? Does that make sense? Okay. So so what's next? Okay. Yeah, so any questions on the story up to this point? Okay. So, right. So let me walk through some of the important, there are 5 important properties that this object, this covariant derivative operator satisfies. You don't have to memorize these 5, but let's just say you should remember that there are 5 of them. And probably when you go ahead and do calculations, whatever it is you do will be, you'll be able to follow your nose and it'll work out right, and it'll be because of these 5 properties. Okay, the 5 properties are going to come back a bit later. Okay, so property number 1, which is not actually number 1, let's call it property number 0. The very first line up on the top there. The covariant derivative depends, it's very local. The idea is that this derivative is very local. So it depends on the vector v, not in a whole region, like not along the curve, but at the point P only. And it also depends on y, the vector field y, also in a very local way. It only depends on the first order information of y. It doesn't depend on second derivatives of y, it doesn't depend on y at a number of different points. It always depends on the derivative of y to first order, y to first order along the curve. So the covariant derivative is very local. Okay, so the 5 properties. So, right. Okay, so let me leave the number 1 is somehow the easiest, but it's also the deepest and hardest in some strange way. So maybe I'll talk about the complication of that one in a second. Okay, number 2. As defined, my operator, oh crap, there's another typo on these slides. This D should be a nabla, should be an upside down triangle. Sorry, I changed notation halfway through making these slides. Okay, anyway, so the covariant derivative satisfies these various properties. Okay, so yeah, so as defined, it's linear in this slot here, this differentiating slot, right? Because the derivative differentiation is a linear operation. You differentiate the sum of 2 functions with the sum of the derivatives. You differentiate a function times a scalar times a real number. It's the real number times the derivative. So you have linearity in this differentiation slot. And also because of the properties of ordinary derivatives, you have the product rule, or the Leibniz rule, the product rule for functions. So the derivative of a function, a scalar function times a vector field, is the function times the derivative of the vector field, but then it's also the derivative of the function times the vector field. And this is the ordinary scalar derivatives that we saw earlier. Okay, so the property number 4 is a generalization of something which is true in Euclidean space. Again, more or less the product rule. But let me just explain what's going on here. So in Euclidean space, if I have the inner product of 2 vectors, let's say v1 and v2, or y1 and y2, right? This is the sum of y1 ith component times y2 ith component, sum from I equals 1 to 3, right? And if I now differentiate this, I go, let's say, so I'm going to go dv of this thing, y1 comma y2, which, as you know, is d by dt of y1 along a curve, y2 along a curve, at the end of t equals 0. So this is basically d by dt of the summation of yi1, yi2. And then I'm just suppressing the C of t in there. We know it's there, so I'm going to need it for what follows. Okay, so I'm basically differentiating this product, right? So again, I'm going to use the product rule here. So this is, what is it? It's two terms. I equals 1 to 3 of dyi1 dt at t equals to 0 times yi2, and then plus the second term, another sum from 1 to 3 of yi1. Now it's di2 dt at t equals to 0. So I got a sum of two terms. And this sum of two terms, if you just look at what the terms are, right? This is the vector y2. This is the vector dvy1. And this is the vector y1. And this is the vector dvy2. So this is the inner product of two terms. It's dvy1, inner product y2, plus y1, inner product dvy2. Okay. So this is a formula that differentiation, this special kind of differentiation satisfies. It's kind of, it follows from the product rule. But actually to highlight it, I highlight it as a special property. So I'm not going to call this the product rule. I'm going to call this the metric compatibility property. It's to say that the covariant derivative is sort of compatible or operates or interacts in the nicest possible way with the inner product. And all this rule number 4 is saying is that that happens in the surface definition also. In other words, I can scratch away Euclidean space and put covariant differentiation here, and I can put a del v here. And because the formula for differentiation involves d by dt along a curve, and then projection in the tangent directions, the same formula holds. Okay? So this metric compatibility property holds for del as well, the covariant derivative. Property number 5 is the so-called torsion-free property. Let me just describe what it says. It involves two things. It involves my little box here, and it involves this down here. So the torsion-free property is saying that if I take the commutator of the derivatives. So in other words, I have two vector fields. I differentiate the vector field y in v1 and then v2. That's the first term. And subtract the derivatives in the opposite order. That's some formula. And well, what does it equal? It equals the derivative in the direction of the Lie bracket of v1 and v2. Okay, so right now just ask me to swallow some terms. I haven't explained anything yet. Yeah?
Do you have a good intuition for this formula?
Yes,
like what
I will.
it's telling you? Yeah.
But I won't do it now.
Okay.
What I want to say is this formula has got a lot of baggage behind it. And I don't want to talk about it at the moment. And so instead I'm just going to tell you that there's this fifth property out there which has to do with differentiating the commutator of two derivatives. And it relates to the Lie bracket, which is the definition of this Lie bracket of the two vector fields on a function is defined as the commutator of the scalar covariant, create scalar derivatives, blah, blah, blah. I'll explain this in a handout. I'll post this online. I'll give you some intuition for it online. All right? So there'll be a supplement on the Lie bracket at some point. Suffice it to say, there is a such thing as the torsion-free property, which is property number 5 on this list of properties. Oh, in fact, there is something that I can say, which may maybe give you a proto intuition for this thing. For property number 5. Here's my intuition in quotes. It's going to be an analogy. So, apples are to oranges like giraffes are to mobile phones. That kind of analogy. In other words, it's not going to mean too much until you read my, my document online. But anyway, here's the intuition. Okay, so we know this, right? D squared f by dxi dxj equals to d squared f by dxj dxi for all scalar functions that are, let's say, C2. Partial derivatives, second partial derivatives compute, right? Or in other words, we can say d by dxi, d by dxj, minus d by dxj, d by dxi as an operator acting on functions equals to 0. Right? Okay, well, the analogy is that what this is to scalar functions, property 5 is to vector fields. For covariant differentiation on vector fields. So somehow, this is an important structural conditions that partial derivatives satisfy. This is an important constraint. It's an important feature of partial derivatives. The Hessian matrix, the matrix of second partials, is symmetric. And this is just an important thing, right? Well, there's a huge amount of material about Lie derivatives and Lie brackets and the torsion-free property and blah, blah, but it's somehow basically, it's property 5 is basically taking care of the commutativity of second partial or second derivatives, second covariant derivatives. The structure that underlies the relations and the constraints among second derivatives, second covariant derivatives. Okay, so maybe that's the in quotes intuition I'm going to give for that property 5 at the moment. There'll be more online. Okay, so far so good. Okay, one last thing which we haven't covered yet, and that's property 1. So when I was writing this document, and whenever you read about these properties in different geometry textbooks, of course property 1 is like the most trivial property out there. And I sort of fell into that trap as well, but it isn't actually trivial. There's actually something going on that needs a little bit of thought. So what I want to say is the directional derivative in the direction v1 plus f times v2 is equal to the directional derivative in v1 plus f times the directional derivative in v2. And actually that does kind of make sense if you think about it in R3 and you write the formula down and so on. Does it make sense? People sort of believe that that's the way the matrices work out? What's the directional derivative? It's like the gradient of f, inner product, v1 plus f. Sorry, should write this down. What's the directional derivative? So in Euclidean space, what's the directional derivative? So your dv of some function, let's call it, what are you going to use it? dv, what are you going to use it? H. This is equal to the derivative matrix of H transpose this vector. Right? And of course it's linear. Why wouldn't it be linear? Of course it's linear. What could possibly go wrong? Okay, well you tell me what can go wrong. Well, this is completely correct in R3. There's nothing wrong with this. I'm just saying there's something we have to think about in surfaces. What is it? Yeah? Okay, that's a good point. What happens if f is badly behaved? Probably something like, probably you can engineer a situation where this fails. Absolutely true. But you can also do that in R3. There's a different point that I want to get at. Can you think some more? How do we define derivatives on a surface? What object do we use as a little helper object to define derivatives on a surface? Yeah, that's right. We used curves. We used a curve to define a derivative, right? We needed that helper curve to express correctly the notion of a derivative. Okay, so here's the problem. Or in fact, can somebody express the problem to me? Okay, suppose I have a curve which generates V1. So here's a curve in space which makes V1, has a tensor vector V1. Draw a picture of that. Here's my curve which generates V1. Here's my curve which generates V2. This vector in here, I don't know where we're going to put it. We're going to put it in this direction. This vector here is V1 plus F V2. And the question is, what's the curve? What's the curve? We define derivatives in terms of curves. If I'm going to prove a theorem about, if I'm going to prove property 1, I better have a curve which generates V1 plus F V2. Do you guys see the problem? This is not clear what the curve should be. In R3, we kind of got around that because we had a slightly different definition for partial derivatives. And, I mean, for D8, for derivatives, we could use the chain rule, and we can use partial derivatives to get around this problem. We have different definitions. But on surface, we don't really have it. So there's a bit of an issue. So I'm not going to go into this any further. I'm just going to say that the intuition is, to first order, none of this matters. Another thing I can say is, all of this can be defined in terms of a parameter domain, and you prove that the definition is independent parameterization. And over in the parameter domain, the R3 intuition holds, except in R2, and there it doesn't matter either. So this ends up not being an issue, but it's certainly something which should cause us concern when we first look at it. Okay, so let's just leave it there. Okay, so the covariant derivative satisfies these 5 properties, and plus we have this idea of how local it is. Okay, so moving forward. The next thing to do is study covariant derivatives from the point of view of the parameter domain. So I told you there's always several ways of doing this. You can either do a geometric definition and then check parameters, check what it looks like in the parameters, or you can do a parameterized definition first and then prove independence of parameters. We went the first way around. We gave the geometric definition. So that means what we have to do now is check what all this looks like in the world of parameters. Okay, so this involves a fun calculation. I have to say, I think it's a fun calculation. It's nice to do. And it also introduces these things which you see floating around different geometry textbooks, the so-called Christoffel symbols. They're always indicated by gamma. They have 3 indices. Sometimes it's 3 downstairs and 1 upstairs. Sometimes it's sometimes it's 2 downstairs, 1 upstairs. Sometimes it's all 3 downstairs. Okay, so I want to walk through this calculation because it's a good one to do. Okay, so the situation is we have our surface, we have our parameter domain. We make the parameter domains to be bigger, right? Okay, so up top we have a curve, we have a vector, and we have a vector field. That's up top. Well, downstairs you have all the same stuff, except this looks a bit different because it's been pulled back into the parameterization. So down in the parameter world, you have, which is it's a subset of R2, right? The parameter space is 2-dimensional. So you have your curve in the parameter domain, you have your vector here, and then you have a vector field along. You have a vector field, non-constant, changing, right? Vector field. So you have the vector field y, and you have the vector v. But the versions of these things, as they're expressed in the parameter domain, you pull them back to the parameter domain. Okay, so let's do the calculation as sort of follow our noses with this calculation. Okay, so what do? Well, first thing is you express V in terms of a basis. Sorry. Yeah, okay. Sorry, so V is, yeah, sorry, I need to add one more thing here. Okay. So we've got my vector, let's call this E1, which is the vector 1, 0, and let's call this guy here E2, which is 0, 1. These are the standard basis vectors in the parameterization, and they get pushed forward to a basis at every point, right? So the basis is E1, which is D, the parameters acting on E1, and E2, which is the differential of parameter matrix parameterization acting on E2. All right? So a parameterization gives me a basis. Okay? And what I can do is write write the vectors in terms of that basis. So this ends up being, never mind where it's located. It's located at this point P here, which is a point U, some U in the parameter ring, and we have 5 U's in P. Okay, so let me write V in terms of the basis, and again, let me write Y in terms of the basis. Okay, and now let's compute del V of Y. Okay, so this is del, and V gets replaced by summation AI EI, and Y gets replaced by summation, let's just change letters to keep things simple, BJ, or to keep things clear, BJ and EJ. So change dummy variables, dummy instances. So I'm just making my straightforward replacements. And now what I use is property 1. So this is one of the properties. There are 5 properties. Property 1 gives me linearity in this bottom slot. So summation AI del EI acting on summation BJ EJ. Okay. So far, so good. Now this is summation AI, open a big bracket. The next thing I'm going to use is, well, linearity in the inside slot here, this inside place. Use linearity here. But because the BJs are a function, they vary along the surface, I need to use the product rule in the BJs as well. I can't just use linearity, I have to use the product rule. Okay? So I get summation AI on the outside, then EI acting on BJ times EJ plus BJ, and then what I have left over, I have del EI acting on EJ. Okay? So this is property, what would they be? They'd be, I guess, 2 and 3. 2 and 3. So I use properties 2 and 3 to evaluate to go from here to here. Okay, now what? Well, now we have to introduce some stuff. So right here, right there, this thing is tangent. Because by definition it's tangent. The covariant derivative is by definition the tangential part. So therefore it's expressible in the basis. So because it's tangent, I know I can express it in terms of that basis. So therefore I have some expression, even though I don't know what it is yet, I have some expression which looks like this vector here, this thing here, is a linear combination of the basis elements. And the coefficients of that linear combination are the so-called Christoffel symbols. So this is summation k from 1 to 3. Okay, so this business here gets replaced by the Christoffel symbols. Yeah, okay. Right. And I guess this is my formula. So maybe, yeah, this is my formula. I'll explain this in a second. But my formula is essentially here. I've expressed, okay, it's not quite the formula. Let me just write over on this side. Just so it's closer to this, so I don't have to do as much explaining. Yeah, okay, so what I've got is summation, I've got that formula way down there, I need to rewrite that. Okay, so let me change the dummy variables, let me change the j to a k, and let me replace the Christoffel symbols in there. Right over here, I'm going to replace this j with a k, just so that the sum looks uniform. So what I've got is a sum over k on the outside, open bracket, and then I'm going to pull the ek outside. So this is EI acting on BK plus Christoffel symbols, gamma I, J, K, and then I have AI, BJ. So that thing down there becomes this when I change the dummy variable on the first set of beads. Okay, right. So what's this? This is the derivative of the BK function in the EI direction. Which is dBK dUI in the parameter domain. Right? In the parameter domain, the E1 direction is little e1 or just 1, 0. And big E2 in the parameter domain is little E2 or 0, 1. So in other words, direction derivative in E1 is partial derivative d by du1. And direction derivative in E2 is partial derivative d by du2. So that's why I can replace this quantity with that quantity if I decide to work in the parameter domain. Okay, so the Christoffel symbols arise in this way. They come from working this stuff through using a basis provided by parameterization. Okay, so far so good? Okay, next slide brings us to the fundamental lemma of Riemannian geometry. So what basically this fundamental lemma tells us is that we've done this right. There is one and only one way to define covariant differentiation on a surface if you want those 5 properties to hold. And those 5 properties were the most reasonable things that you could expect for a differential operator to have, or a differentiation method to have, and furthermore they directly extend to from the Euclidean space differentiation. So, the lemma says that the induced metric G, together with these 5 properties, determine a unique covariant derivative. That covariant derivative is the one we've defined. It's called the Levi-Civita connection. And the way you know it's unique, the way you prove the theorem, is you establish a relationship between the gammas, the Christoffel symbols, which is the only sort of missing ingredient in this formula. The only thing that we can't say exactly what it is, where it comes from. We express these Christoffel symbols, the last missing ingredient, indirectly as a formula in terms of the derivatives of the metric. So it turns out the Christoffel symbols in this lower IJK version, which I'll tell you in 1 second, in this version is equal to this linear combination of derivatives of the metric tensor. So it turns out these gamma lower IJK are the inner products of these derivative objects with the basis vector, and you get the gamma upper K Ij, which is the ones that are appearing on blackboards or whiteboards, as this other linear combination with the metric components. I'll explain this in a handout as well. We're getting to the point where I need to explain why this G inverse appearing all over the place. Before it wasn't so necessary, and I didn't want to confuse this with extra stuff, but we're getting to the point where we need to understand why G inverse shows up all the time. Don't worry about that for now. What you need to get from this slide is the 5 properties give you a formula for the gammas in terms of the derivatives of the g's. So the 5 properties determine this intrinsic covariant derivative. Okay, now we can come back finally to the point of the lecture, the loose end that I wanted to address in this lecture. So remember, so far, the geodesic equation has been this thing up here. This k vector is perpendicular to the tangent plane at every point. Well, I'm now in a position where I can rewrite that in terms of intrinsic things. Okay, how do we do it? Well, first of all, k being perpendicular to the tangent plane means, well, what's k? K in the arc length parameterization is gamma double dot. So gamma double dot is perpendicular to the tangent plane. And that means its parallel part is 0. Okay, we're getting closer. What is gamma double dot? Well, gamma double dot is the Euclidean derivative of gamma single dot in the direction specified by gamma single dot. Like it's the second derivative, right? So you have to take gamma dot and differentiate it in the direction of itself, in the direction of gamma dot. Right? So I've got curvature. I've got gamma double dot, acceleration vector, perpendicular to the surface, means parallel part is 0, means parallel part of this d gamma dot is equal to 0. But now my definition comes into play. My definition was that this right here, the parallel part of the Euclidean derivative, is the covariant derivative. So actually my covariant derivative equation for the geodesic equation, the covariant version, is this here. So there you have it. It's an intrinsic equation. Even though it started off as an extrinsic thing, it's actually an intrinsic equation. It's the covariant second derivative of gamma is 0. And furthermore, if you use the Christoffel symbols and stick this thing into a parameter domain, you get this equation right here. One equation for each k. And there should be a summation in front of this, summation over I and j. So, like I said, a system of second order ODEs. After you express this, pull this back to the parameter domain, use these techniques to express this in terms of the Christoffel symbols. Okay? All right, so mission accomplished. The geodesic equation is something which is intrinsic to the surface. Geodesics are intrinsic objects, not extrinsic objects. Okay, so I got 5 minutes left. I need to do a little bit of groundwork for Justin's next lecture. And how many slides do I have left? 2. Okay, good. One slide more or less with the substance that I need. Okay, so in order to pave the way for Wednesday's lecture, I need to tell you a little bit about the so-called standard vector calculus operators and how they look on surfaces. Okay, you guys remember divergence, gradient, curl, all those vectors? Well, that's what this is about. Okay, so the first thing is the gradient of a function. Well, what's the gradient of the function supposed to be? Well, it's supposed to be, you're supposed to say, express the function as level sets, as a mountain range, right? Where large values of f equal higher up the mountain. And the gradient of f is the vector field which tells you what direction to walk in order to increase and climb to the top of the mountain as quickly as possible, right? It's the steep direction of steepest ascent. That's what the gradient is, right? Furthermore, well, the way we get at this in calculus is you define directional derivatives as given a function and a curve in direction v, the directional derivative on the left-hand side is this, but on the right-hand side it's equal to the inner product of v with something. And that something is the gradient. And of course, how do you make this number maximal? How do you make this inner product maximal? You move v in the direction of gradient. So you make it maximal. You make it minimal by going in negative to gradient. So you have a direction of steepest ascent and descent. So the gradient is defined geometrically as the thing whose inner product gives you the directional derivative. And of course, in Euclidean space, the gradient is the transpose of the derivative matrix. The derivative matrix is a row, and you want the gradient to be a vector, so you need to take its transpose. That's how you get it. Okay, but the thing is, on a surface, you can't take transpose like that. You can't do that. Because on a surface, well, sorry, in a parameter domain, I mean, you can't really do this. Because orthogonal doesn't mean what you think it means in the parameter domain anymore, right? In the parameter domain, you have the metric g. And g is different at every point. And so parallel directions might be, these two vectors here might be orthogonal, right? These obtuse angle might be orthogonal. Orthogonal no longer means what you think it means in the parameter domain. So how do I make the same thing happen in Euclidean space? I mean, in the parameter domain. In the parameter domain, the vector that I need to call the gradient is still use the same geometric definition, except replace inner product with g. And so the thing that makes this formula hold is if you define the gradient vector to be df, the derivative matrix, except multiplied by the inverse of the matrix. Again, I'll explain why the inverse of the matrix again keeps showing up all the time. But here's a first clue why it's happening. Because orthogonality down the parameter domain doesn't mean what you think it means. So in order to have a vector for which this formula is true, in the parameter domain where the metric governing things is g, this is the formula for the gradient. Okay, so the upshot of this slide is that if we ask you to compute the gradient of a function on a surface using this parameterization, you find the derivatives of the function, and you also have to find the metric g. And then you come up with this vector here. So this vector here is the gradient in the parameter domain. Does that make sense? So the gradient is different than what you think, because the gradient requires orthogonality, and orthogonality is different than what you think. Okay, so that's the gradient. Now, maybe my last slide is just flashing this up here. I want to say this principle, the principle that orthogonality is a bit different than what you think, means that the formulas for all of these famous, in quotes, differential operators are different. So you have the gradient on a surface, you have the divergence on a surface, and you have a Laplace operator on a surface. You have a curl too, but don't worry about that for now. In each case, there's a geometric definition. So there's always something like concrete, geometric, that doesn't depend on parameterization to fall back on. In the world of the gradient, the gradient is the vector whose inner product gives the directional derivative. The divergence is defined as, well, the divergence of a vector is the sum over this set of derivatives there, where EI is an orthonormal basis. And it turns out this is independent of parameterization. So that is actually, or it's independent of choice of basis. So it too is a geometric object. And the Laplace operator is defined then recursively in terms of this and that. It's the divergence of the gradient of f. So you have these three geometric definitions, and in Euclidean space, where the metric is trivial, and orthogonality means exactly what you think it means, you can derive straightforward formulas, the usual formulas you've seen before, in terms of, for these operators. But on a surface, in the parameter domain of a surface, it's different. The gradient looks like this and involves g. The divergence looks like this and involves g in this via the Christoffel symbols. And the Laplace operator, this should have been this is upside down, it should have been an ordinary triangle. The Laplace operator of f is a complex formula involving g and the Christoffel symbols. So the upshot of this slide is all three of your favorite operators carry over to surfaces, except you have to be careful how you compute them. They involve g, the metric. The reason is the notion of orthogonality has changed. Okay, so Justin will take it from there on Wednesday. So thanks a lot. That's it. See you guys in a couple days.